It is late. You're probably staring at a screen right now, maybe a dark-themed IDE.
Yeah, maybe a terminal window just blinking back at you.
Right, exactly. And as developers, as software engineers, we just live in a world of APIs. Like if you need natural language processing
Yeah,
today,
just make a fetch call.
yeah, you make a fetch call to a massive server farm somewhere, you wait a few hundred milliseconds, and you get a beautifully formatted JSON response back.
And then you just move on to the next Jira ticket.
Exactly. We use these massive language models every single day, but let's be honest right now. Building one from scratch, taking it from a completely blank slate to a functioning text-generating model.
It feels impossible for a single dev.
It feels like dark magic. For most of us in standard software development, it feels like this untouchable black box. Like it's locked away in some enterprise data center and requires, I don't know, a billion-dollar compute cluster to even boot up.
It really does feel that way. There's this undeniable mystique around the entire field, like this pervasive sense that you absolutely need an advanced math PhD and a literal warehouse full of hardware just to get a basic hello world out of a neural network.
Right.
But the reality, especially when you scale the architecture down to a manageable size, is it's profoundly different. Once you strip away the hype, it's just engineering.
It's just code.
Yeah, it's data pipelines, memory management, and optimization.
And that is exactly what we are doing on this deep dive tonight. We are taking the engine completely apart.
Bolt by bolt.
Literally. We're looking at the exact practical mechanical steps of training a mini LLM, taking it from a purely theoretical academic concept to an actual running training loop. And here's the part that is going to change how you view this entirely. We are looking at a process that takes hours.
Not months, not weeks.
Hours. And as a software engineer, you know the immense value of a tight feedback loop, right?
Yeah.
When you set a tangible goal like spinning up a model in an afternoon, it completely demystifies the problem.
It totally shifts it from a massive multi-year research project into a highly complex but totally achievable weekend build.
Yeah.
But to get there, we really need to break down the actual engineering pipeline. We have to unpack how to curate the data set, how to strictly define the hyperparameter architecture, the sheer mechanical brutality of the training loop itself.
Oh man, the loop is wild.
It really is. And finally, those critical floating point optimizations you absolutely must implement to keep your hardware from just melting down.
Right, so let's start at the very beginning of that pipeline. Before you write a single line of your training loop in PyTorch, before you even think about spinning up a GPU instance, you need the fuel, the raw material.
The data set.
The data set. At its core, a data set for an LLM is just text in the form of raw bytes. It can come from anywhere, really. The internet, massive libraries of books, public code repositories, whatever you want the model to ingest.
But this introduces a massive challenge when we are explicitly trying to build a mini LLM.
Right, because of the size constraint.
Exactly. We need a data set that is large enough to actually train the model to understand language, but strictly small enough to remain practical.
So we don't end up waiting 6 months for the script to finish.
Yeah, that tension, large enough to build a statistical map of language, but small enough to compile in an afternoon, is the first real architectural hurdle you face. Because you aren't just feeding this system a dictionary, You're feeding it structure.
No, wait, let me push back on this a bit. Because when I am onboarding a brand new junior developer to my team, if I want them to be useful quickly, I don't sit them down and say, okay, first read the entire internet, go read Wikipedia, then read The Lord of the Rings, and then eventually look at our code base.
Right, that would be terrible management.
It would. I give them the specific code repos they need. I give them the API docs, the exact narrow context. So if we are just dumping raw bytes from random novels and mussy internet scrapes into this mini LLM, aren't we risking building a model that is just a confused master of none? Like, why not just feed it strictly technical documentation if we want a technical model?
It is a great analogy, but here is where we have to fundamentally separate standard human learning from machine learning.
Okay.
When you onboard that junior developer, they already possess a fully trained biological neural network.
Well, most of them do.
Yeah, ideally. They already know English. They already understand logic, context, syntax, abstract problem solving. But a completely initialized blank slate model, it knows absolutely nothing.
Right.
It doesn't know what a noun or a verb is. It doesn't know that a Python function requires strict white space indentation. It is literally just looking at a massive array of numbers.
Right. It's starting from absolute mathematical zero. It doesn't even know what a word is yet.
Precisely. So why do we need that massive variety of books, internet scrapes, and code? because that broad variety is what teaches the matrices the fundamental structure of language itself, even at a mini scale.
Okay, so how do books specifically help with that?
Well, books are critical because they teach the model long-form narrative coherence, how an idea in paragraph 1 relates to an idea on page 10.
Oh, wow.
Yeah. And the internet teaches it varied tone, diverse vocabulary, Q&A formats. And then code repositories are incredibly valuable because they teach the model strict, rigorous, logical structure and formatting.
So if you only fed it your specific API docs,
It wouldn't have enough varied structural data to understand the underlying statistical relationships between tokens. It would just overfit.
meaning it would just memorize the docs.
Exactly. It would memorize your docs line by line and completely fail the moment you asked it a slightly novel question.
Ah, I see. So the variety isn't about giving it a bunch of useless trivia. It's about giving it a wide enough structural foundation so it can actually learn how to predict the next token accurately across different contexts.
Right.
It's learning the scaffolding of human thought.
That's a great way to put it. Defining practical means finding a highly curated Goldilocks zone. You build a data set that has enough of that varied structural fuel books, code, web to build a robust statistical map, but you brutally cap the total gigabytes so your machine isn't churning endlessly.
You filter for extremely high-quality bytes, basically.
Yes. Ensuring the diversity is there, but strictly limiting the volume.
Okay, so we have our perfectly curated, structurally diverse data set sitting on our hard drive. But we can't just write a while loop and fire the data at the GPU. We need the rules of engagement,
We have to set the architectural dials.
right? In the machine learning world, these are the hyperparameters. And the rule here is absolute, right? You must choose your hyperparameters before you write the actual training loop,
Yes, non-negotiable.
because these settings dictate the literal shape of the model, and getting them right is what ensures this mini LLM trains in hours.
They're the mathematical bedrock of the entire system. Hyperparameters dictate the exact physical shape of your neural network. We're talking about defining the embedding dimension.
Which is exactly how many numerical dimensions you use to represent a single token in vector space, right?
Exactly. And we're talking about the number of attention heads, which dictates how many different context clues the model can mathematically look at simultaneously.
But this is where my standard engineering instincts get a little defensive.
How so?
Well, in modern back-end development, I'm used to agility. If I'm building a distributed microservice architecture, I tweak configurations on the fly all the time.
Right.
I dynamically scale Kubernetes pods, I inject new environment variables, I hot reload my configurations without dropping traffic. So why do we have to hard lock these hyperparameters before the engine even turns over?
Because it's not a microservice.
But what happens if our initial configuration is just totally wrong? Like, why can't we dynamically adjust the attention heads while the loop is running?
I completely understand that instinct because dynamic allocation is, it's the hallmark of modern software. But training a neural network is not like routing web traffic. Think of hyperparameters less like environment variables and more like defining a strict database schema or manually allocating fixed memory buffers in C.
Oh, okay. Fixed memory buffers. That makes total sense.
Right. When you define those hyperparameters, the layers, the embeddings, the attention heads, you are defining the literal sizes of the matrices that will reside in the GPU's video RAM.
And those have to be allocated up front.
Exactly. If you start your training loop, your model begins doing matrix multiplication. It begins adjusting millions of tiny internal weights based on that specific, hard-coded mathematical shape.
So if I suddenly decide to change the embedding dimension midstream,
The math instantly shatters.
wow.
If you change the dimensions of your matrices while the loop is running, it's exactly like changing the size of a struct in C while a program is actively running.
Your pointers are suddenly pointing at garbage data.
Exactly. The matrices literally cannot be multiplied together anymore because the rows and columns no longer align. The weights the model spent the last hour meticulously adjusting are suddenly mapped to a totally different physical architecture.
Sounds catastrophic.
It is. You can't just adjust the dial. You have to wipe the VRAM, scrap the entire model, and start over from zero.
Okay, that is a harsh reality check. It really highlights why the architecture has to be so heavily premeditated.
Yeah.
You were doing the tensor math up front to ensure the matrix multiplications won't crash.
Right.
And you're doing it to ensure the total parameter count is small enough to actually be processed in a few hours on your local machine.
Exactly. You calculate the total parameter count based on those hyperparameters. You look at your available GPU memory and you say, yes, these matrices will fit and I can process them in a practical time frame.
Which brings us perfectly into the execution phase, the engine room.
Here we go.
We have our data set on disk, we have rigidly defined our matrix dimensions with our hyperparameters, and now we build the loop that actually does the heavy lifting. And the numbers involved here are just staggering.
They really are.
This single training loop runs hundreds of thousands of times. Each individual iteration processes exactly 65,536 tokens.
Yep.
And on a modern GPU, pushing that massive block of data through the entire network takes perhaps 200 to 500 milliseconds.
It is an almost incomprehensible amount of computation happening in a fraction of a second.
Let's actually visualize this math because the scale is wild. 65,536 tokens. A token is roughly a word. So we were talking about a block of text roughly the length of a short novel.
Right.
And the training loop is mathematically digesting that entire short novel every half second. It does this, updates its weights, and then grabs the next short novel.
Over and over.
As a back-end developer, I know what that kind of I/O throughput looks like on a system level, and it is violent. If you tried to push that through standard architecture, the CPU would bottleneck instantly. Why are we so entirely dependent on a modern GPU for this? Like, why not just a massive CPU cluster?
It comes down to the fundamental difference in how CPUs and GPUs handle mathematics. If you try to run this training loop on a CPU, even like a massive 64-core enterprise server CPU, you will never even get close to that 500 millisecond benchmark.
Why not?
Because a CPU is a genius at complex branching logic. It handles if-else statements, context switching, and highly sequential tasks brilliantly. But pushing 65,536 tokens through a neural network doesn't require branching logic.
Oh, it requires parallel matrix multiplication.
Exactly.
Right, it's doing millions of relatively simple addition and multiplication problems at the exact same millisecond.
Yes. A modern GPU doesn't have a few genius cores. It has thousands of relatively dumb, specialized cores that excel at doing the exact same mathematical operations simultaneously. It takes that massive matrix of text, slices it up, hands a piece to every single core, computes the forward pass, and aggregates the results in parallel.
Wait, let me think through the logic of the batch size itself. Why 65,536 tokens?
Yeah.
It's not just about pushing data fast for the sake of speed, is it?
No, not at all.
Because if the model looks at the data, makes a prediction, checks how wrong it was, and updates its weights, I guess if it only looked at, say, 10 words at a time, the feedback would be incredibly noisy.
Oh, very noisy.
The statistical map would be chaotic because 10 words don't represent the average structure of the language, so it needs that massive bulk of 65,000 tokens so it can find the true statistical average of its errors before it updates its weights.
That is a phenomenal deduction. You just described the core mechanism of batch processing and gradient descent. Yeah. If your batch size is too small, the gradient, which is the direction the model adjusts its weights, bounces around wildly based on the quirks of a single sentence. Processing 65,000 tokens simultaneously provides an incredibly stable, smoothed-out statistical average.
That makes perfect sense.
It forces the model to learn the underlying universal patterns of the raw bytes in that 500 millisecond window, rather than just memorizing the noise of a specific sentence.
The scale of the parallel math is literally what creates the stability of the learning. That is beautiful engineering. But pushing a 65,000 token batch through a network every 500 milliseconds creates an absolute nightmare for memory bandwidth.
Oh, absolutely.
I mean, the VRAM has to be screaming just trying to move those floats around.
Yeah.
To survive this brutal loop without the hardware crashing with an out-of-memory error, we have to look at the final critical optimization.
The secret sauce.
The secret sauce of modern LLM training, mixed precision.
It is the single most important practical technique you will implement. Without mixed precision, hitting that hours rather than months goal locally is completely impossible.
Okay, but hold on. Let me put this in the context of standard deterministic software again. In regular development, messing with floating point precision is how you introduce catastrophic, incredibly hard-to-track bugs.
Oh, yeah, totally.
If I'm writing a physics engine for a game, and I decide to drop my velocity variables from 64-bit precision down to 16-bit precision just to save memory, things drift. Calculations get sloppy.
Ships start flying through walls.
Exactly. Ships fly through walls because the rounding errors accumulate over thousands of frames.
So are we just intentionally cutting corners on the math here to save VRAM and keep our loop under 500 milliseconds? Like, how does introducing that kind of mathematical drift not completely destroy the model's brain over hundreds of thousands of iterations?
That is exactly the right question to ask. And it highlights the fundamental difference between deterministic and probabilistic systems.
Okay, unpack that. Well, in a physics engine or a banking application, every single decimal point is sacred. But a neural network is inherently dealing with fuzziness. When it calculates that gradient how much to adjust its weights, that calculation naturally contains noise.
Right.
It doesn't need to be perfectly precise to the 15th decimal place just to know it needs to move generally left. What engineers discovered is a brilliant compromise. Not every step of the training loop requires high 32-bit precision.
So how does it know when to be precise and when to be fuzzy? What is the actual mechanism?
The architecture maintains what we call a master copy of the model's weights.
Yep.
That master copy is always stored in highly precise 32-bit format. That ensures the long-term memory of the model never suffers from accumulating rounding errors.
Got it.
But when it comes time to do the actual heavy lifting, that brutal 500 millisecond forward pass where it multiplies the 65,000 tokens across thousands of matrix dimensions, it dynamically casts the data down into 16-bit precision.
Oh, I see it. It is essentially dynamic caching for floating point math.
Yeah.
You use the lightweight 16-bit format to blast through the massive memory-heavy compute phase. You calculate the gradient quickly, and then you take that tiny little update and apply it back to the high-precision 32-bit master weights.
You absolutely nailed it. By doing the bulk of the intense matrix multiplications in 16-bit, you literally cut the VRAM memory bandwidth requirement in half.
Wow.
You double the throughput speed on the GPU's specialized tensor cores, and because you are updating a 32-bit master weight at the very end of the loop, you completely avoid the catastrophic physics engine drift you were worried about.
That's incredible.
You optimize the pipeline strictly for speed where it matters and preserve precision where it counts. That specific engineering optimization is the bridge that turns an impossible workload into a mini LLM you can actually spin up on a weekend.
That is just phenomenal systems design. It is taking the harsh physical constraints of the hardware and writing an elegant software solution to bypass them. It is just so satisfying to see how this works under the hood.
It really represents the moment machine learning matures from pure academic theory into hardcore, deeply optimized software engineering.
So let's look at the complete picture of what we've built tonight. We started by meticulously curating that just right data set, blending books, internet scrapes, and strict code repositories to give the untrained model a diverse structural foundation.
Right.
We talked about the rigid discipline of defining your hyperparameter schema up front, locking in the physical dimensions of your matrices before a single piece of data moves.
Crucial step.
Then we dove into the engine room, breaking down the sheer parallel processing power of pushing 65,536 tokens through a GPU to find a stable statistical average every half second. And finally, we unpacked mixed precision, the dynamic floating point optimization that protects your memory bandwidth and keeps the entire system running fast enough to finish in a matter of hours.
When you look at it end to end like that, the magic completely fades away, but the beauty of the engineering remains.
It truly does.
Yeah.
As a software engineer, walking through these exact mechanisms means a mini LLM isn't an untouchable billion-dollar black box anymore. It's just a highly optimized system.
Yeah.
It has tightly controlled inputs, a rigid architectural schema, an execution loop built on parallel matrix multiplication, and incredibly clever memory management. It is a system you can architect, you can compile, and you can run locally on your own machine.
The barrier to entry has quite literally never been lower, provided you respect the mathematical and hardware constraints we laid out today.
But before we officially sign off, I want to leave you with one final provocative thought, a new angle to ponder as you stare your terminal tonight. We talked about how that training loop sequentially digests massive chunks of data, updating its internal weights every 500 milliseconds.
Yep.
So consider this. How does the sequential order of your training data fundamentally alter the foundational logic of your final model?
Ooh, that's interesting.
Right. If you structure your loop to feed it millions of lines of strictly typed, highly logical code repositories first, and then feed it expansive creative narrative fiction second, does it learn differently than if you completely reverse the order?
Wow.
Does early exposure to rigid, uncompromising logic fundamentally wire the mathematical foundation differently than early exposure to creative storytelling?
Yeah.
It is an architectural question that goes beyond just the PyTorch syntax and straight into the fascinating philosophy of how an artificial system actually learns to think?
It is a profound question. It forces us to realize that the temporal nature of training data might be just as important as the data itself.
Definitely something to mull over as you optimize your own training loops this weekend. Thank you for hanging out with us tonight, for looking past the REST APIs, and for diving deep into the actual architecture with us. Keep building, keep optimizing, and we will catch you on the next deep dive. Have a great night.